Hello, and welcome to another exciting episode of Introduction to Applied AI. I'm your host and your professor, Dr. John Baugh. For this lecture, we're going to be discussing generative AI and VAEs, or Variational Autoencoders. So, this lecture introduces a new category of AI systems. The focus shifts from using models to understand how generation works. We will explore how machines create new data rather than classify existing data. So why does this lecture matter? Well, generative AI underlies many modern AI systems: text generation, image generation, audio and video synthesis. Understanding generative foundations helps explain model behavior. This knowledge improves how applied systems are designed and evaluated. So, how does this lecture fit into the course? Well, previous lectures focused on prompt design, output control, chains, tools, and agents. This lecture is going to take a step back and examine what generation means at a conceptual level and how generative models differ from other AI approaches. The goal is deeper understanding, not new tooling. So, learning goals for this lecture are to describe what makes a model generative, explain the role of probability in generation, understand the idea of latent space and representation learning without requiring additional mathematics, or at least of advanced mathematics. We will discuss basic math that you probably have already encountered, and to identify where VAEs fit in modern AI systems. So, LLMs and generative AI, the relationship. Generative AI as a broad category. Generative AI refers to systems that create new data. The generated output is based on patterns learned from training data. The goal is not prediction or classification. The goal is, in fact, synthesis. So, where do LLMs fit into this? Large language models, or LLMs, are generative models. They generate sequences of text. Generation is performed one token at a time, and each token is chosen based on probability. This could be viewed even as advanced autocomplete. This makes LLMs a specific type of generative system. So, what do we have when we look at text generation versus general data generation? Well, LLMs generate text. They generate things like words, sentences, and structured text formats like JSON or XML. Generative AI also includes models, not just like LLM, but models that generate images, audio, video, scientific or numerical data. Different data types require different model designs. How does LLM generation work at a high level? LLMs learn statistical patterns in language. Generation is based on predicting likely next tokens. Again, back to the advanced autocomplete idea. The process involves controlled randomness. It samples from probability distributions, and that allows outputs to vary while remaining coherent. What LLMs do not explain by themselves? Well, LLMs do not model all types of data. They do not rely on explicit latent spaces in the same way. LLMs still learn internal representations, but generation is not framed as sampling from a low-dimensional latent variable model, which we'll talk a little bit more about later. Understanding generation more broadly requires probability theory, representation learning, and latent variable models. These ideas apply beyond language. Why does this distinction matter? Well, applied AI systems often combine multiple model types. Understanding generative foundations helps with debugging unexpected behavior, evaluating outputs, and designing reliable systems. This lecture will expand the mental model introduced by LLM-based tools that we've looked at before. So, generative models and probability foundations. So, we have to distinguish between discriminative and generative models. Machine learning models can be grouped by what they learn. Discriminative models focus on classification and prediction. Okay, so for example, you have a set of data you're trying to organize by different classes, or we're trying to look at previous data and say, okay, well, the housing market looked like this up to this point. What will it look like in the future based on previous data? That's prediction. Generative models will focus on learning how data is distributed and producing new examples from that distribution. What generative models learn? Well, generative models learn patterns in data. These patterns describe how likely certain data is. The model does not memorize examples, it learns relationships and structure. That enables the creation of new data that resembles the training data. So why is probability required? Generation involves uncertainty. There are many valid outputs for the same input. Probability allows the model to represent multiple possible outcomes, choose among them in a controlled way. Without probability, generation would be rigid and repetitive. Randomness versus structure. Well, randomness alone produces meaningless output, so structure alone produces identical output. Generative models balance both. Structure comes from learned patterns, and randomness comes from sampling. This balance enables variation without the chaos. Probability distributions as intuition. So we will look at very, very basic math soon. Many of you have had some experience with statistics and probability, probably before looking at this lecture, but we're not going to dive super deep into the math. We're talking about mostly intuitive notions and a little tiny bit of math later on. So probability distribution describes where data tends to occur. Some values are more likely than others. Sampling means selecting values based on likelihood, and more likely values are chosen more often. This idea applies across all generative models. Sampling and generation. So generative models do not choose a single correct answer. They sample from a set of possible answers. Sampling introduces variation between runs, and constraints shape what kinds of output are possible. So learn structure and model design are involved with this. So why does this matter for later topics? Well, probability underlies all generative approaches. Latent spaces rely on probability to enable generation. Training objectives are expressed probabilistically, and understanding this foundation prepares us for variational autoencoders and beyond. Now, on to this word or this phrase we've been discussing, latent spaces and representation learning. So what is a latent space? A latent space is a hidden representation learned by a model. It encodes important features of the data. Okay, that's key. Encodes important features of the data. The latent space is not directly observed. It is learned during training. It's kind of hard for us to visualize as humans, but it's different qualities of the data that are being stored in the memory of the model, or the storage of the model as it trains. So generative models operate within this space. So here's a little example here. This is a 2D latent space representation visually. You have the latent dimension on one side, latent dimension 2 on the other, 1 and 2. Now, what do these dimensions even mean? The model knows. It may not be something that we would look for or that we would describe succinctly as humans. This is an MNIST-like data set, and if you're familiar with the MNIST data set, it's basically a bunch of handwritten data. It's thousands of examples. I believe there's like 70,000 examples with, I think, 60,000 or something in the training and then 10,000 for testing. But anyway, this is a very common first run for different machine and deep learning topics, is to use the MNIST data set. Well, anyway, this is like an MNIST-like data set. This isn't the actual MNIST, but this is showing you kind of what it might look like. So you'll see that, for example, 9, the number 9 different samples were found to be the number 9. Those are the ones clustered in yellow. Ones for 8 are in kind of a lighter greenish color, etc., etc. So each point represents a data example encoded into latent space. So, for example, a digit that someone wrote. Points that are close together represent similar inputs as far as the model is concerned. Points that are far apart represent different inputs. Clusters form naturally based on learned structure. In other words, similar examples are grouped together. Smooth movement through the space changes outputs gradually. So, why do models use latent representation? So What do we actually mean by latent? Well, latent means hidden, really is what it means. And humans might classify things with specific named features, for example, like circle or purple, bent, rough, etc. Those are interpretable, discrete, linguistically labeled from our perspective as humans and chosen deliberately. So we decide in advance what matters. What the model does instead is that it's not really told what features exist. It doesn't. We don't tell it look for circular things, look for purple, look for rough. It makes many observations about multitude of examples, and it looks for statistical regularity. So it learns internal variables that explain variation, and those internal variables are the latent variables. So they don't often or don't always have human readable names. Okay, they're numerical. They often combine multiple human concepts and capture similarity even when we cannot describe it cleanly. So the model does not think necessarily purple or bent. It thinks in terms of patterns of variation. Okay, so real world data is high dimensional, and working directly with the raw data is inefficient. Latent representations compress the information and preserve important structure. The compression reflects understanding, not loss. So representation learning is the process of discovering useful features. Those features are learned automatically. Again, they're not pre-described or prescribed like we would as humans, purple, bent, circular, things like that. The model decides what information matters. This differs from hand-designed features, as mentioned. No manual feature engineering. So similarity and distance in latent spaces. Well, points in latent space represent data examples, and distance reflects similarity. Closer points are considered more similar, and distant points are more different. This allows models to reason about relationships and even across unseen examples. A useful latent space is structured. So small changes in the latent space should produce small changes in the output. Smoothness allows interpolation and gradual variation. Unstructured spaces lead to unstable generation. So interpolation as a test of understanding. Interpolation means moving between two latent points. Generated outputs change gradually along the path, and this reveals whether the model learned meaningful structure. Sudden jumps indicate poor representation learning. What about latent space and embeddings? Well, embeddings are a form of latent representation. They both encode meaning in numerical form and both rely on distance to represent similarity. Latent spaces generalize this idea beyond text, as we'd mentioned before, with audio and images and other data types. So why does latent space matter for generation? Generation happens by sampling in the latent space, and the structure of this space determines output quality. A well-learned latent space enables novel outputs, meaning unique or new outputs. That's what we mean when we say novel in this context. Coherent variation, and this concept is foundational for variational autoencoders. So let's start with just regular old idea or regular old concept of autoencoders before we get into VAEs. So an autoencoder is a neural network, so it's a deep learning model. Anytime you see neural network, you should think deep learning. Okay, it goes beyond just, it's a subcategory of machine learning. It's a neural network, so it's a bunch of nodes organized into a neuron, we call them neurons, organized into a network. And it's trained to copy its input. That's what an encoder is supposed to do. The output attempts to reconstruct the original data. The model is composed of two main parts, an encoder and a decoder. So what does the encoder or decoder do? What do they do? The encoder compresses the input data into some form, and the compressed representation is called a bottleneck. The decoder expands that representation and tries to create the original space. The bottleneck forces the model to learn useful features. So the thing that it's learning is actually how it turned the compressed version back into the original version or something similar. Then it can rate it by how well it did, and then it keeps trying and can learn new ways of doing it. So the reconstruction objective. Autoencoders are trained to minimize reconstruction error. A lot of times with machine learning and deep learning models, we try to minimize like a loss function. We're trying to minimize or reduce the difference between what is supposed to be the answer and what the model predicted. So that is, there's many different techniques for this, depending on the types of data and all sorts of things like that. But ultimately, that's the idea, is we want to minimize some sort of error. And in this case, it's the reconstruction error. So the goal is for the output to resemble the input. This encourages the model to capture important structure and ignore noise. The model's not trained to generate new data. Why autoencoders, specifically just autoencoders, are not generative. Each input maps to a single latent point. There's no notion of uncertainty, and random sampling is not supported. New data cannot be generated reliably. Arbitrary sampling produces meaningless outputs. The latent space problem. Well, autoencoder latent spaces may contain gaps. Some regions correspond to valid data, others produce invalid data, or invalid outputs, rather. The model has no incentive to organize the space. Memorization versus generalization. Autoencoders can overfit the training data. So they might do a perfect reconstruction, and that does not imply that there's actual understanding on the part of the model. The model may memorize patterns instead of learning structure, and that limits its usefulness for generation tasks. Why do we need something more? Well, we want a model that supports generation. The latent space must be structured and continuous, and sampling should produce meaningful outputs. And these requirements motivate variational autoencoders. That's our next topic. So, what makes an autoencoder variational? A variational autoencoder modifies the basic autoencoder idea. The key change is how the latent space is represented. Instead of encoding to a single point, the model encodes to a probability distribution. So each input maps to a probability distribution. The distribution represents the uncertainty involved, and this allows multiple plausible encodings. Generation becomes possible through sampling. What the encoder produces in a variational autoencoder. The encoder outputs two values for each latent variable, a central value and a measure of spread. These values define a probability distribution. The distribution describes where valid encodings are likely to exist. What about sampling in the latent space? So a latent value is sampled from the distribution. Sampling introduces controlled randomness, and different samples lead to different outputs. This enables variation during generation. So how or why does sampling enable generation? The sampling allows exploration of nearby latent regions, and similar samples produce similar outputs. New data can be generated without copying inputs. Generation becomes smooth and continuous. How does the decoder work in a VAE? Well, the decoder receives sampled latent values, and it reconstructs data from these samples. The decoder does not know the original input, it just relies on the latent representation, that compressed version that we talked about. And that forces meaningful structure into the latent space. Why does distribution matter? So distributions prevent isolated latent points. Nearby latent values produce related outputs, and the latent space becomes navigable. This supports interpolation and exploration. What about uncertainty as a feature? Well, uncertainty reflects ambiguity in the data. Not all input maps to a single correct encoding, and VAEs model this uncertainty explicitly, and that actually improves robustness and generalization. So we talked about autoencoders, we talked about VAEs. How do they differ? Autoencoders encode to a fixed point or fixed points. VAEs encode to distributions. VAEs support meaningful sampling, and autoencoders do not guarantee usable latent spaces. So why are VAEs, as opposed to regular autoencoders, actually generative models? New data can be generated by sampling latent distributions. The decoder transforms samples into outputs. The generation process does not require original inputs, and that makes VAEs true generative models. Training objectives and trade-offs up next. Why do training objectives matter? Well, the generative models must be trained with clear goals. These goals shape how the model behaves. For VAEs in particular, training balances multiple objectives. Understanding these objectives explains the model trade-offs. Reconstruction as a training goal. As we discussed earlier, reconstruction is one of the goals here. So the model attempts to reproduce the input data. So the decoder doesn't see the input data, and it tries to reconstruct it based on the latent representation. Reconstruction quality measures how accurate the output is. Okay, so basically a judge comes by and says, okay, this is a good representation or a bad representation with a specific value. It says this is this far off, or this is that far off, or this is this close or that close. And based on that, it can improve its performance. Better reconstruction means important features were captured, and the decoder can use the latent representations effectively. Why reconstruction alone, though, is not enough. Perfect reconstruction can be achieved by memorization. Remember, we talked about memorization and generalization. Memorization does not support generation. A model trained only for reconstruction may overfit the training data, meaning it'll only memorize what's in the training data and won't be able to generalize, and produce poor results when sampling. So what about structuring the latent space? Well, VAEs include an objective that shapes the latent space. The goal is to encourage organization and continuity. This prevents isolated latent regions and large gaps with no meaningful outputs. A structured space supports reliable sampling. What about balancing competing objectives? VAEs optimize more than one goal at the same time. Improving reconstruction may reduce structure. Improving structure, though, may reduce reconstruction accuracy. So they are often competing interests. Training tries to find a balance between fidelity, meaning accuracy to the original, and things of that type, and the ability to generalize, where it isn't just memorizing. Trade-offs in practice. Well, too much emphasis on reconstruction, you produce sharp but inflexible models, and too much emphasis on structure produces smooth but blurry outputs. Blurry doesn't necessarily mean actually blurry, although it could with images, depending on what the situation is. It just means not really what we wanted. It doesn't really match what we asked for. So those trade-offs explain common VAE behaviors. Why this design is intentional. So no single objective produces good generative behavior. Trade-offs reflect real-world uncertainty, and the training objective encodes design priorities. Understanding this helps to evaluate generative models. So what about interpreting the math behind VAEs? In a VAE, latent variables are random variables. Each latent variable follows a probability distribution, and the most common choice is the Gaussian or normal distribution. This is defined by the mean and defined by a variance. The math represents uncertainty, not noise. So what the model actually learns. For each input, the encoder learns a mean value and a variance value, and these values describe where valid encodings are likely. Sampling uses these values to generate latent points, and this links probability directly to generation. So what is the mean? You probably are familiar with it, but the mean is the average of a set of values. It represents a central or a typical value. It's a measure of central tendency. So example data set, you've probably worked with these when you did mean, median, and mode in different math that you've done. But anyway, the example data set is 2, 4, 6, and 8. Who do you appreciate? Dr. Baugh. The mean is computed as add all values, divide by the number of values. And the formula looks like this. So we use the Greek letter mu, and that equals 1 over n, or 1/nth, of the sum of I equals 1 from, rather, I equals 1 to n of the x sub i's. You can kind of think, if you're coming from computer science background, that this is a little bit like a loop. Okay, so it's looping, and it's going from x sub 1, x sub 2, x sub 3, all the way up to x sub n, whatever that n value might be. And then dividing by 1 over n. So as an example, if we have a data set 2, 4, 6, 8, we would just sum the values. Okay, that's the loop. And then we have the number of values is 4. That's our value of n. Divide the total sum divided by the number of values, and we get 5. So that mean is the center of the data. Variance is the spread around the mean. Okay? It is based on the distance from the mean. So using that same data set, and we know the mean is 5 from previous, each value is compared to the mean. The variance formula looks like this. Variance is represented by sigma squared, and that's 1 over n of the I equals 1 to n of the x sub i's minus the mean. Okay, so here's an example. We would take each of the values 2, 4, 6, 8, subtract the mean. You'd end up with -3, -1, 1, and 3. And then you take those values and you square each of them. You'll notice that, you know what? Here, something's wrong. This should be squared. Let me fix that real quick. The magic of screencasting. I fixed it. You have to actually square each of these differences here. And that gets rid of the negative, of course. So you end up with 9 plus 1 plus 1 plus 9. That's all 20, right? Because 9 plus 1, 1 plus 9, 2 tens, that's 20. 20 divided by 4 is 5. So in this case, the variance is also 5. So the standard deviation is also a value you might come across, and this is basically the square root of the variance. It's sigma itself, okay? So sigma is obviously equal to the square root of the variance, which is sigma squared. And that's 2.24. So how does variance lead to blurry outputs in VAE? VAEs generate data by sampling from a distribution. Each sample represents a slightly different version of the input. The decoder must handle a range of possible latent values, not a single fixed point. This causes the features to be averaged across samples. The averaging smooths fine details, and the smoothing appears visually as a blur. So in this case, we're talking about an actual blur, whereas with data across a wide range that may not be visual is more of a metaphor. It basically describes a loss of sharpness, specificity, or decisiveness, not necessarily fuzziness that you can see. Okay, so blur reflects uncertainty in the latent representation. It's a design consequence, not a model failure. So mean and variance in VAEs. Well, in a VAE, the encoder does not output a single value. It outputs parameters of a distribution, a mean value and a variance or standard deviation. The mean represents the central location in latent space and the most typical encoding for the input. The variance represents uncertainty, remember the spread, in that encoding, okay, and how much variation is allowed during generation. How this math enables generation? Well, latent values are sampled using the learned mean and variance. Sampling near the mean produces typical outputs. Sampling farther away from the mean introduces variation. This process allows new data to be generated and smooth transitions between examples. Without the mean and the variance, sampling would be unreliable and generation would break down. So, strengths, limitation, and modern context. What VAEs are good at? VAEs learn structured latent representations. They support smooth interpolation between examples. Small changes in latent space produce gradual output changes, and this makes VAEs useful for understanding data structure. Representation learning strengths. VAEs capture high-level features of data The latent space reflects semantic similarity, and these representations can be reused for clustering, visualization, and downstream tasks. Generation is only one use case. So, common limitations, though, of VAEs include generated outputs can appear blurry. And again, if it's not an image, we're talking about the lack of sharpness or specificity or decisiveness, as mentioned before. Fine details are often lost, and sharp boundaries are difficult to model. These issues are not bugs, they just result from design trade-offs. Why VAEs were not replaced but extended? Limitations motivated new generative approaches. Generative adversarial networks improved output sharpness. We will see more on that in a future lecture. Diffusion models improved sample quality and stability, and each approach addresses different weaknesses. So, how VAEs are used today? So VAEs are often part of larger systems. They're combined with other models, and common modern uses include latent representation learning, scientific data modeling, and anomaly detection. So VAEs in the current GenAI landscape, VAEs are not obsolete. They provide interpretability and structure, and they remain valuable where the data is complex, explainability matters, and controlled generation is required. So, preparing for the next topic, understanding VAEs highlights key generative challenges: sharpness versus stability, structure versus flexibility. These challenges lead directly to adversarial approaches like generative adversarial networks. So, connecting back to applied AI. Why generative foundations matter? Applied AI systems rely on generative behavior. That includes, of course, the LLMs that we've discussed earlier in the course. Generation, is not limited to creative tasks. Outputs influence the decision, automation, and user trust. Understanding generation improves system design. An applied example, anomaly detection with VAEs. So VAEs can be trained on normal system behavior, and the model learns to reconstruct typical patterns. Normal inputs reconstruct with low error. Unusual inputs would reconstruct poorly. So, for example, features do not match the learned patterns. High reconstruction error signals that there's an anomaly. This is used in applied settings such as manufacturing quality control, network intrusion detection, and financial fraud detection. Latent space versus the token space. VAEs operate in latent spaces. LLMs operate in token spaces. Both represent data numerically, and both rely on probability to generate outputs. The sampling controls the variation. Generation models in real systems. So real-world AI systems combine multiple techniques. A single application may include LLMs for the language part, latent representations for structure, and retrieval for grounding. Generative foundations unify these concepts and components. Implications for applied AI design. Generative behavior must be evaluated carefully. Understanding trade-offs helps. So diagnose failures, tune system behavior, and how to choose appropriate models. Theory informs our practical decisions. So how does this prepare us for what will come next in the course? Generative challenges do not end with VAEs. Output quality, stability, and realism remain open problems. Next approaches that we will discuss in this course explore different solutions. So this foundation prepares us to study adversarial training. As a summary of this lecture, generative AI focuses on creating new data as opposed to just discriminative AI. Generation relies on probability and controlled randomness. Latent spaces provide structured representations of the data. VAEs are a foundational generative model. So understanding VAEs. VAEs, again, extend autoencoders by modeling uncertainty, and whereas autoencoders are not generative models, VAEs are generative models. Latent variables are represented as distributions rather than just a single value. Sampling enables generation and variation, and training balances reconstruction and structure. Why does this all matter for applied AI? The central tenet and central concept and topic of our course. Generative behavior affects real systems. Model design involves trade-offs, and understanding foundations improves reliability. These concepts prepare us for more advanced generative models. So that's what I have for you for this particular lecture as far as this recording is concerned. I hope that this is informative and it helps you whet your appetite for future discussions, especially when we talk about adversarial networks and things like that. So I will see you in the next lecture. Bye-bye.